plus excitations. But in general, any initial state that you give to the evolution in the full Hilbert space, if you let it evolve, it just lose and lose information. There is this irreversibility in the dynamics, and at the end of the day, it goes for a fixed point in your Hilbert space. And then it goes for what we call the steady state. Usually this steady state is classical, or it has no quantum interesting properties anymore. However, under certain conditions, we can try to use this dissipation to go towards interesting steady states, and not necessarily mixed state. We can also try to aim at pure steady states with non-trivial quantum properties by our Lindbladian quantum dynamics. Okay, so we call this approach sometimes as a synthetic open system dynamics, because they do not occur naturally in the physical system. We really need to go for the experimental platforms and try to engineer specific couplings between the constituents, or sometimes also we call as a reservoir engineering, because you really need to fine-tune the parameters in there. Okay. So the idea of these dark states, or dark states being used for a beneficial form in your task, it actually dates back from studies in laser lights coupled to atom systems. It's not a very new idea, but recently the main goal is that these works here, they were more approached for independent atoms, and now we are going to the many-body settings. But let me just recap these previous ideas, or the initial concept that was trying to use this, using the dissipation to generate pure steady states and non-trivial quantum properties. So essentially you have this ensemble of atoms here which do not interact with each other. So you can think just about single atom physics in this case in here. And then you shine some laser to these atoms. They are going to absorb this laser, and then at some point they're going to emit also the laser light. But then before the laser reaching to the atoms, you put this polarizer in order to let it pass only circularly polarized light to the atoms. Okay, so essentially your atoms can be many different degrees of freedom, but for certain atoms you can have these two specific hyperfine levels where either your atom has a magnetic moment down or up, but also it can have some other degrees of freedom, such as the total angular momentum, and also if they are in the s, p, or any higher order orbital. And for some atoms, you have this structure here, where you have the same total angular momentum with different s or p orbitals. They have a different energy. And each one of them, you have this degeneracy of up and down magnetic moment. Okay? So if you shine then a laser light that is circularly polarized to your system, it means that the laser light now has also an angular momentum that is positive. Okay? Then if your atom is in this ground state configuration here, it can only absorb the laser light if it is in the down magnetic moment, because it needs to conserve the total angular momentum of the system. So it needs to absorb a positive angular momentum from the light, but since this excited state is also with a fixed angular momentum that is the same as the ground one, it needs to go from down to up and absorb. You cannot make this different path here from up to down, because it would have to be in a negative angular momentum for your laser light. So you have some kind of super selection role here for the absorption of your energy from the atom. And then once the atom is in the excited state, it's still interacting with the electromagnetic field, and at some point you're going to have some spontaneous decay of this atom. But the spontaneous decay now, it has no superselection role. It could be either decaying to the same where it came, and then you shine the same angular momentum for your light, or it could also decay to up, and then you shine a negative angular momentum for your light. Okay? But then you see the following process that is happening here, right? So you're always exciting atoms that are in this level here to the top, and then 50% of them is going to come back, and 50% of them is going to this different energy level in here. So at the end of the day, if you make this procedure many and many times, all of the atoms, they are going to be in this specific configuration in here. So this is going to be what is called then the dark state of our system. So this is a way to engineer the dissipation, and the dissipation is given by the interaction with the atoms here, in a way that you can produce now all of your ensemble of atoms in the same ground state configuration. Okay? So this is a way to think in a clever way how to produce states with quantum properties by just using the dissipative in your favor. Okay, so and then, as I said, the idea is to generalize these things for the many-body realm. Essentially, in this case here, you can treat them as independently, but now we want to understand if we can also play shining some laser or put your many-body system to interact with dissipative environment. What can we do in this sense? So we know that the dynamics is driven by the Lindbladian master equation. This is our first assumption. We have the coherent term from the Hamiltonian, and we have the dissipative term from the Lindblad jump operators. And the goal here is trying to produce some pure states that are dark states. So at the end of the day, we want that the Lindbladian superoperator acting in my pure state, it needs not to evolve. It needs to be totally equal to 0. So mathematically, how can I do this? So there is one very simple and direct form, is that if you impose that the Hamiltonian commutes with your dark state, in other words, if the dark state is an eigenstate of your Hamiltonian, then you kill this first part here in the dissipative dynamics. And if the state lies in the kernel of your jump operators space, and by kernel, I mean that is a 0 eigenvalue of my operator, then you see that I kill also all of the correlation, all of the dissipative part in here, right? Because you always have an L operator acting from the left, or an L operator acting from the right, in both cases here. Oh, it's missing 1/2 here. But here also you have L from the left, and then the commutator L dagger from the right, okay? So this is one very simple condition that would satisfy the possibility of creating a dark state as your steady state. Actually, this is just a simpler case, but there's some generalized form to give these two equations here. It's a bit more interesting than this, but for our purpose here, just these two conditions are going to be sufficient. Okay? So then how to engineer the jump operators such a way that we create interesting steady states or interesting kernel pure states. And from now on, I'm going to talk only about purely dissipative dynamics. So we are going to say that somehow you engineer this open system dynamics in a way that the L operators here, or the dissipative part, it's much more dominant than the Hamiltonian part. So essentially, you are very strongly coupled to this dissipative environment. And then we just say that the Hamiltonian is going to be equal 0 in our dynamics. We just need to care about these L operators here. In principle, it would be the worst case, right? So we just have dissipation, but we see that's not always the case. So we need to satisfy that psi lives in the kernel of my jump operator, which, in other words, it means that if I make the expectation value of this guy here, the bracket of it, we see that is equivalent of saying that my psi state, it's a 0 eigenvalue or a 0 energy of this Hamiltonian in here, right? So I say that this L dagger L is some kind of a Hamiltonian energy component, and this is essentially equal 0. So since L dagger L, an operator that you make dagger with itself is by definition a positive operator. It has only 0 or positive eigenvalues. So then if you have the condition that they need to be in the 0 eigenvalue of these operators here, it means that the dark state is a ground state of this operator in here. Yes? So you're weakly coupled in order to derive the Lindblad master equation, but still this weak coupling is much larger than the internal Hamiltonian dynamics of your system. So yeah, it's strongly compared to the Hamiltonian, but it's weak compared to the Lindbladian derivation. Okay. Yeah. So this gives us some interesting relation or a simpler relation in order to understand how to produce interesting pure dark states. Because now we have that the dark states are going to be the 0 eigenvalues or the ground state eigenvalues of these terms here. And then we can say that equivalently, we can build this parent Hamiltonian that is just getting all of our jump operators in the dissipative equation and making a Hamiltonian-like for them. And the ground state and the steady state, by definition, is the 0 eigenvalue of this guy here. That means that we have the ground state of this Hamiltonian. Then we can somehow map all of our discussion about closed system Hamiltonians in frustration-free cases, where you can have or not some interesting ground states there, and you just produce the corresponding jump operators that are going now to generate, by definition, some interesting steady states for open system dynamics, okay? But of course, that some important questions here is, given that you have this type of parent Hamiltonian, how good or how easy or how physical is the implementation of these jump operators in here, right? And then we need to think about how local are these Li operators in my Hamiltonian. Can we use some experimental platforms to engineer them? Yes? I'm sorry? So it's because this is the class of, there is this class of Hamiltonians that if your ground state is the minimal energy for all of your terms in the Hamiltonian, yes. And then this is the class that we call as frustration-free Hamiltonians. Okay, the ground state, it minimizes all of the terms of your expansion in the Hamiltonian. They share at least the ground state eigenbases. Not necessarily all of the eigenstates, yeah. But the ground state is shared between all of them, yeah, that's it. Yes, this is a strong condition. And that's why it's interesting to think on what is the class of these guys here. And perhaps they are also trivial, but that's not always the case, because this is a very special condition indeed. Yeah, so we need to think, I mean, okay, so we have this relation. How local is this if we can implement in the experimental platform? And of course, I mean, if we have some non-trivial many-body correlations or interesting physics in this class of Hamiltonians here as well. Okay. And indeed, the answer is positive, as is the title of this lecture. We can find some topological phase that can be written in this form of frustration-free Hamiltonians, and which have non-trivial topological properties, such as edge modes, parafermionic Majorana fermions excitations. So let's just then review this literature, or a bit of what I call by topological fermions, or this module, this frustration-free module. So the model is what we call by the Kitaev chain. It was proposed in 2001 by Kitaev, especially for applications in quantum computation. It's a very simple theoretical model that it was proposed in the sense that you have just a single wire, a single one-dimensional chain, that the fermions, you can consider effective spinless fermions in your chain. And they are in contact to some superconductor material in a way that this superconductor would induce some effective, coherent superconducting interactions or pairing interactions among the spinless fermions in your chain. Depending how these pairing correlations are induced in your wire, if they are strong enough, you would have also the superconductor appearing in your wire, but with these non-trivial properties that at the edge of your wire, you have these weird or different particle excitations that are the Majorana fermions appearing at the edge of your system. So the Hamiltonian is very simple. So if you have this effective model for your Hamiltonian in the wire, that is just one-dimensional spinless chain. Okay, we have seen also in the first lecture in the context of Anderson localization, where your fermions now, they can make the hopping between nearest neighbor sites. This is just this first term here. You can also have some chemical potential that in order for your fermions to be occupying or not one physical site. But then you have this new term here that we didn't see in the first lecture that is induced by this superconductor proximity here. And what it does, it creates pair of fermions at neighbor sites, or the Hermitian conjugated, it annihilates pairs of fermions at neighbor sites. And this is essentially what perhaps many of you have already seen in the BCS theory. So this leads to a superconductor because this pairing here tends to really pair your fermions in some specific momentum. Okay? And the good thing of this model also is that this is a quadratic model in the fermionic operators. By quadratic, it's when you have just pairs of fermionic operators, either dagger-dagger or dagger and annihilation, but it's just two of them that apply to your Hamiltonian. If you have a fermion-Hamiltonian that is just pairs of fermionic operators, then you can always have some easy solutions in some cases, in some sense. Okay? So we say that this model here is solvable. So what do I mean by solvable? And here perhaps I'm going really to the calculations. I said that I would not do this, but I'm doing just for this part here. When we say that the system is solvable, it means that we can make a transformation of bases in my fermionic creation and annihilation operators in a way that is simpler to see what is going on in the eigenspectrum of my Hamiltonian. So the transformation is what we call as Bogolyubov-de Gennes transformation, and it's just two steps that you need to do. The first one, you say that I don't want to see this Hamiltonian in the real space basis, where the creation and annihilation operators, they are acting at physical sites, J, J+1, J+2. I go for the momentum space. So I make this transformation here that I create a new momentum fermion operators that are just the Fourier transform in the real space for my fermionic operators. Okay? So this new set AK here is also a set of fermionic annihilation and creation operators that satisfy all of the anti-commutation relations. And then in a second step, we make this, what is now really the Bogolyubov-de Gennes transformation, that I say that I want to look for more general kind of fermions operators that are not only creation or annihilation operators, but they can be a superposition of annihilation and, it should be a dagger here, and a creation operator. So it's something like a particle hole excitations that could be occurring in your system in here. The good thing is that these Bogolyubov operators, they are also fermion operators, in the sense that they satisfy the anti-commutation relations that we expect for any fermion particle. So they anti-commute for any different indexes, and the annihilation with the creation, they satisfy the delta Kronecker if they are with the same index. So it's just a change of basis in my whole set of operators. The good thing is that if we use this change of basis, the Hamiltonian is written in this very, very simple form. That you see that now I don't have the whole expansion of many different terms here. I just have a single term that is NK, NK, dagger and annihilator. Okay? With some energy that is the energy of each one of these Bogoliubov excitations that appear in my system. And then by definition, this is frustration-free Hamiltonian, because the ground state wants to minimize each one of these at the dagger at the K operator. That's the connection that we can do then with the dissipative dynamics, okay? The ground state is going to be the one, the new vacuum of this Hamiltonian is the one that every time that you see for the presence of this Bogoliubov excitation, there is none of them, so it's really just the minimizing this whole energy in here. And then you can obtain the ground state and derive the whole phase diagram, what are the different phases that could appear in this model here. So you see somehow what we expect, that if you look here, for example, that the chemical potential is very, very strong, it means that the particles don't really want to be at the physical sites there. There is a high energy cost to be occupying the physical sites. Then we have just a trivial or an insulator phase there. Okay? But on the other case, if the chemical potential is not so high, and we have these pairing correlations between pairs of fermions in the system, we have this different phase here, where you see the appearance of a superconducting phase in our one-dimensional chain. And then this can be just seen, but if you look by looking at the expectation value of, this should be AA, not AA dagger, I'm sorry. There are a lot of typos here. So if we look for the appearance of pair of fermions with opposite momentums, aka A minus K, forget about this dagger here, you see that the expectation value of this guy here is different from 0. So it means that your fermions, they are somehow parent in the momentum plus and momentum negative between them. So you have the superconducting appearing in there. And then let's go back to the dissipation, right? Then we can just use these Bogoliubov operators as our jump operators in the dissipation. If we just assume this mathematically, we have that the steady state is going to be the ground state of this Hamiltonian by our property there. So we have that the ground state is going to be the dark state in this strong dissipative case. But then we go back to the question. Usually these Bogoliubov excitations, as you can see, they are defined in the momentum space, where they are completely non-local along all of your chain. And that's not good in order to generate this experimentally or really physically implement this type of dissipation. So usually they are highly non-local, but that's not always the case. There are some specific points in this phase diagram here where the things simplify considerably, and then we can try to implement this idea. And that's the goal now, to show this thing. For this we go in the Majorana fermion space. That is going to be much simpler to see how these things appear in there. So looking for this different perspective, instead of looking in this complex fermion base, where you have A and A dagger operators that are annihilation and creation satisfying the anti-commutation relations, we just build a new basis that is a simpler basis that we call the Majorana fermion basis. So we say that any of these annihilation or creation operators that is a complex operator in my Hilbert space, if it's a complex operator, it always have a real part, and it can also have a imaginary part. Okay? And then we just decompose in these two parts here. So we say that each one of these operators has a real part that I'm going to call as gamma 2j minus 1, and an imaginary part that is just gamma 2j. So the odd component is the real part of my fermion, and the even component is the, so the odd is the real, and the even is the imaginary part. And then if you look for the property of these gamma operators that appear here, you see that they are also fermion operators, in the sense that they also anti-commute, they satisfy the fermionic anti-commutation relations, but now by definition, these operators, they are real operators, because they are just getting the imaginary and the real part of bicomplex fermions. So in other words, these are fermionic operators, but the creation of one of these excitations is equal to the annihilation of these excitations. So these particles now, they are their own antiparticles. And this is what we call as a Majorana quasi-particle excitation. You can see this in many different forms. Either you can say that this is just half a fermion, because this is when you decompose a physical fermion into different parts. Okay? Schematically, that is going to help a lot to see what is going on in the different phases and how to produce the jump operators. We can always then represent a fermion, that is just schematically by this guy here, by this pair of Majorana fermions, gamma 2J minus 1 and gamma 2J. So for example, if we have a Hamiltonian that is just a chemical potential in a fermion in a lattice site, just a dagger 1, A1, plus some constant, for example, if we do this transformation here, then it just means that we have now a pair of Majorana fermions in the same physical site that has some correlations because they multiply pairwise here in the Hamiltonian energetic cost. Is it okay, guys? Okay, so then we substitute instead the whole Hamiltonian from this fermion basis into the Majorana basis. Then we have a lot of different terms that appear here in the Hamiltonian, but it's essentially just making this, using this equation here into the whole Hamiltonian basis. We see that we have pairs of fermions between the right even to the odd, the next one, the left odd to the right even one, and then the chemical potential is going to do what we did in the previous slides, that locally in the physical site, they add some energetic cost. So you have a lot of Majoranas that are coupled in pairs in your physical chain. So just to recover those trivial phase and topological phase that we found in the Bogoliubov genes, look, for example, for this simpler case, that we don't have hopping, we don't have any pairing coupling between the Majorana fermions or the fermions, then we just neglect these two terms here, and the only thing that's missing is this chemical potential that is giving these interactions of the fermions in the same physical site, odd and even, for the same J, which is then just represented schematically that we have all of these fermions that split into Majoranas, and each one of these two splitted has this energy cost in the Hamiltonian, and then we just need to minimize all of these independent guys here, and the ground state is what we know is the topological, is the trivial phase in this case. Okay. Then going to this topological part of the phase diagram, and that's here very important that we find this, what we call the sweet point of the model. It's when we can kill this term here or this term in here, one of them, for example. So let's say just that we kill the second one and also the chemical potential, meaning that the chemical potential is small, and we have enough pairing correlations to create the superconductor there. But then we see that the Hamiltonian is just a local interaction of Majorana operators, and all of these terms here, they commute to each other, and they are the frustration-free components of our parent Hamiltonian. Okay? So then here in the sweet point, we know that we are in the topological phase, and moreover, we know that these operators here, they are just local operators acting in our Majorana fermions. So let's just put this schematically, going back to the sweet point again. And the only term that survives is this guy in here. And you see that now you split all of your fermions in the two Majorana fermions that described then. But then the interactions between the Majorana fermions is always from the right one of the jade site, so let me say this guy in here, to the left one of the J+1 side. Then you see that these Majorana fermions, they interact in this form here, somehow connecting the two physical fermions, right? But all of them, they come in pairs and do not interact to the other pairs of my system. So in this case, we know that we have in the bulk in here, to minimize all of the energy, we have the superconductor, and then you can go to the Bogoliubov, the genes. For example, you can just write down in terms of the Bogoliubov excitations, you're going to see that this is very simple, but then you already see that the Bogoliubov terms in here, they are just local in the fermionic creation and annihilation operators. So they are just acting in these two pairs that are local in here. And then one very important thing to notice here is that since we have this open chain, we always have the right one to the left from the right from the physical, the left from the neighbor side. But then when you reach to this last one here, since the chain is open, it's not connecting to the first one of my left edge. So essentially, in my Hamiltonian, I don't have this pairing of the rightmost to the leftmost Majorana term. So these two Majoranas that are really at the edges of my chain, they have essentially zero energy in my full spectrum or in my Hamiltonian. So any excitations that I do in these edge Majoranas here, I have no cost. So we are going to have a lot of degeneracies because the appearance of the zero excitation. Or in other words, I have now a Bogoliubov excitation related to these two edge modes here that is completely non-local along my full chain. Okay? And this leads then to a twofold degeneracy. So now I have the ground state that is the bulk superconductor, but also I can have these edge excitations or the Majorana edge excitations in my system that has no cost in my Hamiltonian, and therefore they have the same energy as my ground state. And this is very important. This is for the boost of this idea here. Because now we can say that these two ground states here that are completely degenerate, they can form the basis for my quantum computer. They are my qubit. I can call the ground states as the zero logical qubit, and the one with the edge excitations as the one in my logical qubit. So I have one qubit that you could have also in many different Hamiltonians, but now they are very robust because they come from this many-body phase, from this topological phase, and even if you have some small imperfection in the interactions or how these fermions are coupled in the bulk in here, you still have the degeneracy, you still have a completely qubit, and then you have this fault-tolerant quantum computer in essence. Okay? Okay, so then, how then to generate this type of physics dissipatively? We could use that the jump operators, they are the Bogoliubov excitations in this sweet point case in here. That is just saying that the jump operators, they now both annihilate, leading to a phase of neighbor fermions, or they create without a phase in neighbor fermions. If we can do this in the experimental platform, then we will be very happy. And indeed, there is these proposals by Peter Zoller and Sebastian Dill and collaborators of trying to implement these guys here in cold atoms optical lattice platforms that we discussed, but I'm just going to review a bit briefly here that we have this ensemble of atoms, and we can cool down then for a very, very low temperature using different techniques. And then we just shine laser lights counter-propagating directions in a way that these lights, they create now a small potential that is the optical lattice potential. If the particles, they have very, very low energy, they're going to be trapped in these optical potentials, and you can try to engineer many different models and many different physics in here. And then the idea by Sebastian Diller and collaborators was to use essentially two one-dimensional optical chains. So instead of these two dimensionals, you can restrict to one dimensionals. But then you create not just one, you create two of them. So you create one that is going to be the main one that I'm going to be more interested. And you create an auxiliary lattice in order to help to engineer this specific dissipation that we want to do. In a way that now the auxiliary lattice is in contact to an external reservoir, is in contact to this Bose-Einstein reservoir, but not your main lattice in here. What you can do then is to excite the fermions in your main lattice to this auxiliary one in some specific forms, and then these auxiliary ones are going to be in contact with the reservoir. They are going to be spontaneous decaying towards back your main chain of the system. And then remember, what we want is that we want some excitations such that between nearest neighbors, we can have different phases for these excitations. So you can use some different Rabi frequencies between even and odd fermionic sites here to create then, or to excite then, with a different local phase. So if you have a Rabi frequency with positive here frequency and minus frequency in here, you're going to do exactly this first term of your Lindblad jump operators. And then since this other one, this auxiliary lattice is in contact with this reservoir, is going to spontaneous decay at some point. But now this spontaneous decay has the same probability of going to the right and going to the left. And then you have this spontaneous decay bringing back the fermions to your main chain with no local phase between each other. So what you could do then in this platform is to generate this type of jump operators that excite with local phases and de-excite isotropically back to your chain. Okay? So this is a very clever idea, and you see the similarity with what we want, right? Apart from the fact that here you have a sum of all of them, and here you have a product of all of them. And this is a very important and non-trivial difference, okay? Because in order to go from this guy here, this type of dissipation, back to what we want, if you make a mean field approximation, you can also do a mean field in dissipative systems, such as we did in the time crystal, for example. You see that this term here, within a mean field approximation, it's exactly what we want for the Bogolyubov excitations. So from the mathematical point of view, it's okay, but from the physical point of view, in this case here, we don't have number conservation of the fermions, right? So we are always annihilating or creating fermions. And from this point of view here, we are always conserving the total number of particles or fermions in our optical lattice. And this symmetry in this experimental platform is a very important platform because the atoms, they are really conserved there. We cannot just relax so fast this type of property. And indeed, it's possible to show that if you look for some exact results on this dissipative setting here as compared to the mean field approximation, you see that this conservation is very strong constraint in the sense that using these jump operators, you would still generate some superconducting properties in your chain. Now using only dissipation, that is very, very nice. However, we need this degeneracy in our Hamiltonian or in our steady state in order to have the edge modes. And the conservation of the number of particles simply say that you have always a unique steady state and you don't have these edge Majoranas anymore. So you can create just superconductors there, but not real using for quantum computation because of no edge excitations in the system. So there is this way to circumvent this problem, let me say completely theoretical, that now instead of just having one chain that is coupled to this auxiliary lattice, just like in this case in here, one chain to an auxiliary lattice, you have two chains now that are coupled to three auxiliary lattices. in a way that now your particles, the global particles, can be conserved, but now these two chains here, they can generate a Kitaev-like properties, okay? I'm not going to the Hamiltonian or to the dissipative operators, but just to say that using this theoretical idea, you can conserve the total number of particles in the jump operators. You can have the superconductors in there that we want also, and you can recover the degeneracy of the steady states having these edge excitations there as well. But now we lose completely, not completely, but at least it seems to be not so simple anymore, how to physically implement this type of more general settings in here. Okay. So, I'm sorry? So you can have two if you assume that then you have some exchange of fermions directly between A and B wire here. So the important thing is that you need to generate locally some pairing interactions between each one of your chain, okay? In principle, if you exchange these particles with the auxiliary lattice, they help to generate like pair of hoppings, the excitations of fermions in these two chains, in two sides here, are going to be related to creation of particles in these two sides here as well. So you're going to have something like A dagger, AA operator in here that are going to appear as A dagger operator in the second chain. In the sense that if you look effectively for each one of the chain, you have either creation of pair AA or either annihilation of particles A dagger, for example. And then we recover somehow the physics of the Kitaev model indeed. One way to do this is using the auxiliary lattice that make this effective interaction between them. But that's true, that's true. In principle, you don't need to have this auxiliary in the middle. That's true. And in fact, I think that we even have a more recent paper than this one in 2016 that shows that just with these two here and just one auxiliary lattice could be doing this, bro. Yeah, that's true, yeah, I'm sorry. But the important thing is that you want to generate the locally in each one of the wire. And if you think that of tracing out everybody else, this should be similar to the physics of the Kitaev chain. Okay, so yeah, so let me say that it's not easy to generate these edge modes or these topological edge modes. This is in fact a very big challenge from many, many years that people in the community are facing. And the problem, let me say, is still open to now. So many experimental works have been done, especially in the beginning of 2010, 2012, and so on. And they were really trying to go for this approach of closed system, and then you have the wire in contact to a superconductor. So we have exactly this here in contact to a superconductor. And then you can try to look for signatures of these edge modes appearing in your open wire. As for example, you can look for some spectroscopy of the energy at the edge of your wire and see for the appearance of the zero energy excitations in there. As for example, here you can make the zero bias conductance experience, looking here for some peaks that could appear at zero energy. That would mean that you have some roughly zero energy excitations that could be said that these are the edge modes. There are many experiments looking for these things. There are many discussion. There are a lot of debates and no consensus at all, actually. There's even some retraction papers regarding that they have observed, but now they are not conclusive anymore. They don't know. So the question is still open. And I mean, the main idea here is just to give this different perspective to the same problem. So now we could try perhaps to think, instead of generating these nice excitations in a closed system, we try to look for a completely dissipative system that could still having this kind of important properties in here. Okay. So I think that this is the main idea that I want to talk here. but I still have some time, and then I'm just going to say why these things are nice for quantum computers, okay? So because we said that they are going to be a qubit, that a qubit is protected by topology, so they are very robust to perturbation in your system. But then at the end of the day, we also want to make some operations in our qubits. So we have 0 and 1, but we want to make some rotations of our qubits in the block sphere. We want to make some gates out of it. And then the main thing of these Majorana fermions is because they have particular statistics when you braid them in your chain, okay? In other words, also, I mean, the first step that we are still looking is to look for the presence of these Majorana fermions. That could be very interesting for quantum computations. But once we find these topological fermions here, we want to apply for technology, and then we will have to manipulate also these edge excitations to make the operations in the qubits. And this is going to be the next step to come. So what do I mean by braiding? So imagine that you have these fermions or Majorana fermions or any type of particle in your system, and you want to exchange these particles of position. So let me say that I have gamma 1, gamma 2, and gamma 3, and I want to exchange 2 and 3 by positions. I make the braiding of them, and then I want to exchange 1 and 2 of positions. I'm making the braiding of them. But you could do this in different forms or in different orderings. So you could braid first 1 and 2, and then you braid the second and the third, okay? If your particles are usual fermions, they are indistinguishable for each other, and we know that each one of these braiding here would just generate a minus phase from the anti-commutation relations between the system. So it does not matter if you exchange them in this order, 2 and 3 and 1 and 2 first, or if exchange in 1 and 2 and 2 and 3 first, it would lead to the same result, okay? So in the notation of braiding operations, where Bij means that we are braiding I and j particles, if I do the braiding of 2 and 3 and 1 and 2, this case here, is going to be essentially the same as doing 1 and 2 and then 2 and 3. And this is what we call as you have some abelian statistics for these particles in your system. But the interesting thing of edge Majorana phases or edge Majorana excitations is because they do not satisfy this simple expectation here. So depending on the way that you make the braiding on your edge excitations, you obtain final outputs that can be different from each other. So if you make now the same braiding between them, it could be different from making at the order, the reverse order. Somehow they remember of how they are being exchanged in your system in there. They have some memory of this. And this can be used to make the quantum operations on my qubit in the topological phase, okay? So how we do this if we have a one-dimensional chain, such as in the Kitaev chain? In the Kitaev chain, we have just these two guys appearing at the left and the other one appearing at the right. How do I manipulate them in a way that I can exchange them opposition? So a very simple form or a very interesting idea is just you use what is called this T-junction here. So you create somehow additional leg for your chain in a way that if you want to exchange now gamma 1 from gamma 2 excitations, you first just bring gamma 1 down to your leg, and then you have space to bring gamma 2 to the left part and make the completely braiding, okay? How can you do this physically, let me say? Here you have your Hamiltonian with superconducting properties, with chemical potentials and hoppings and so on. So what you could do is just increase the chemical potential at one of the edges. If the energetic cause now is too high at the left edge, what the Majorana fermions prefers to do is to jump a bit to the right here. So then you somehow shrink your chain a bit to the right, and then the Majorana is just hopping essentially to the right. You increase again the chemical potential in this guy here, and then the Majorana is going to be a bit more on the right. So if you have this manipulation in your experimental platform, you can just bring the left excitation up to any position that you want. Okay, yes? Yes, yes. Yes, because you change the position of the edge, okay? So you can think that what is an edge in your physical system? An edge, the particles say that this is an edge because all around here is not energetically favorable for it, okay? And then what you change is what is the position that is energetically unfavorable for the particle to occupy. So if you increase, for example, the chemical potential in here, so then the particle is going to prefer to stay a bit shorter, okay? If you do this, of course, that you need to have a lot of care to do this because you need to be adiabatically in order to not excite also some other spectrum in your system. But we always have some gap in the Hamiltonian because of the superconductor, so you still have a way to do this in a finite time. Okay, so and then this is the idea. So if you can play with the chemical potential, let me say, in each one of the positions, spatial positions of your T junction, you can do anything that you want regarding exchanging the effective position of your edges and exchanging the effective position of your Majorana fermions. You can bring this guy down, it goes down, and then you bring the other one to the left, and then you bring the guy that was down to the right, and effectively from A to D, you did the braiding of these two particles in the system, okay? Then what happens? I mean, we need to have more Majorana fermions. So the main idea is going to have many chains. So let me say that I have one chain here, and I have a T-junction in order to play with the braidings. I have a different chain here, a T-junction to play with the braidings, and in principle, we want to generate many of these topological phases. Here is just theoretically, okay? And then, what is the effect of braiding then the Majorana fermions in this whole set of many edge excitations? So each one of them would somehow generate an effective qubit, another qubit, and then we can have many qubits in our quantum computer. Okay. So how do I represent a braiding operation in this subspace in here? So it's not so hard to see what's the shape of this unitary here. We just make some reasonable assumptions that we should expect. Is that the first one is that if the braiding is act on the Majorana operators of our system, it acts on these ground subspaces with either no Majoranas or with the Majoranas excited at the edge. So the braiding operator should be described by the set of gamma operators that are the edge excitations on each one of my chain. Moreover, these braiding operations, they do not create new particles. They just exchange the position of my Majorana fermions in there. So for example, if I try to represent the braiding by this type of operators here, as for example, I'm creating a Majorana at some position or some other position, these terms are forbidden because I need to conserve the total number of particles in my full operation. And the only terms then that are going to be allowed is this guy here. It conserves the parity, and you can change the positions of your particles. And moreover, this is a unitary operation. It needs to preserve the probability distribution of my pure state. And we know that any unitary operator can be written as the exponential of a Hermitian term times the identity. Okay. And this Hermitian term is just what is allowed here. I times the product of my Majorana fermion operators. Okay. Then we see the conclusion that the operation of braiding exponential of I times a Hermitian operator. The Hermitian operator cannot create or annihilate particles. It needs to conserve the total number of Majorana fermions. So apart from a phase equal beta, is just equal to the product of them. So the phase I here is going to cancel with the phase I here. So it's just an exponential of a phase times the product of these two Majorana operators. So it's a very, very simple gate that you apply here. And then we can expand here in Taylor expansion, for example, and then you just have these two terms appearing. So cosine of this phase times the identity plus sine of this phase times the product of the two Majorana fermions. Okay, but what is this phase exactly? This phase is going to act in my Majorana fermions and perhaps generate some non-trivial properties. How can we discover what's the phase? So we can first then apply the braiding on the gamma I operator. So if we make the braiding on gamma I operator, and the braiding is taking I to j, so this guy should lead to gamma I operator, gamma j operator at the end, okay? So if I apply the braiding on this physical Majorana fermion here, it should becomes a gamma j operator at the end of the day. So all of this here, that is just using this expression and substituting in my main equation, should lead to simply gamma j operator in here, okay? So perhaps I can open this relation here just to be more simple. So we have that if I apply the gamma I operator with the braiding of gamma ij to gamma ib ij dagger, so this is just expanding the unitary operator. Is going to have some cosine of beta times the identity plus sine of beta times gamma I, gamma j, all of these that multiply to gamma I, and all of this that has the dagger on the right. Identity plus, let me continue in here, sine of beta, and then the dagger of this guy here is just exchanging their position. So then I have gamma j dagger, gamma I dagger, okay? So it's this whole operation that I need to apply to my ith Majorana fermions. But then we remember that the Majorana operators, or these excitations, they are their own antiparticles, so dagger does not mean anything here. For us, we can simplify, and we can then expand this whole thing here. So then we have the identity with the identity that appears here. So we have a cosine square of beta that multiply gamma I. Then we have cosine with my sine. So I have cosine of beta times sine of beta. And then the identity that multiplies gamma I and gamma j I. So then the identity that multiplies gammas I, gamma j, and gamma I. Okay? And this we can also simplify. We know that two Majorana fermions, they anticommute. So I can exchange the ordering of these two guys here in the sense that this is gamma I, gamma j, with a minus sign, okay? And then we know that Majorana fermions, they are their own antiparticles. So if I have gamma I with gamma I, is essentially I'm creating and annihilating this particle 2 times. So this is going to be equal to the identity. So at the end of the day, all of this guy here is just minus gamma I, gamma j operator, okay? And we can play with this idea for all of the other terms. So we have cosine, cosine with cosine, cosine with sine, and then we have sine with cosine, and then we have again the cosine of beta times sine of beta, and now these terms appearing here, times gamma I, gamma j, and gamma I here again. And again, we can make the same idea here, right? So we have the same term in here, and this guy is going to be minus gamma j. And the last term is the sine term with the sine term here as well. So we have sine square of beta that multiplies gamma I, gamma j, and then we have gamma I here again, and then we have gamma j, gamma I. And then it's just manipulating these guys. So we can first do this thing here. We exchange these two, and then we have minus gamma I, gamma j. And then when this guy meet to this guy here, they become the identity. But then we have space for this guy to meet this guy here and become identity as well. And the only thing that's missing is this guy here. Then at the end of the day, all of this here is just minus gamma I operator. So finally, we have gamma I in here and gamma I in here, multiplying a cosine of square of beta minus sine square of beta times the gamma I Majorana fermion. And we have gamma j here, both with the same amplitude, but with a minus sign. And then we have minus 2 sine of beta cosine of beta times gamma I. Okay? And then we just recognize that this guy here is nothing than cosine of 2 beta, and this guy here is not as sine of 2 beta. And this is the equation that appears there for us. Okay? But what we want physically is that when you braid a Majorana operator at the ith site, and the braiding is from position I to j, all of this thing here leads to my Majorana operator now defined at position j. So somehow we need to kill this first term here, and then this is going to constrain the phase possible for our system, and only this guy needs to survive. Okay? Then we already see that beta needs to be either plus pi over 4 or minus pi over 4. Okay. And we can do the same for the other guy. So if we do for braiding the jth Majorana fermion, we apply the same procedure, we obtain essentially the same results, but apart from a different local phase for the braided case. We see then that at the end of the day, the first gamma I need to go to gamma j, and the gamma j need to go to gamma I, but since they are fermionic excitations, you need to have a minus sign between them, and this minus sign appears from this condition of either beta needs to be equal plus pi over 4, then you kill this guy here and a minus sign appear. I'm sorry, it would appear in this case here, or minus beta over 4, and then the minus sign would appear in this case here. So you have this gauge freedom in the definition of your braiding operation here as well. But the conclusion is that the unitary operation of exchanging these two Majorana fermions of position is just the simple pi over 4 phase operation over the Majorana operators. And then if we go back to our system with many edge Majorana operators, I can build then my qubits on top of this. Then I can say that 0 is no presence of edge excitations, and 1 is the presence of the Bogoliubov excitations, or the left and right Majorana fermions. And if you think for these two, for example, configurations of having no Majorana fermions in my chain, it's just the ground states for both of them, and having 4 Majorana fermions for both of the chains. So we have gamma 1, gamma 2 in the form of the Bogoliubov excitations, and gamma 3 and gamma 4 in the form of Bogoliubov excitations. I'm not going to show the calculations here, but it's essentially applying the braiding operator on this basis in here, and it's just, again, manipulating Majorana fermion products and exchanging, just like we did in here. You see that braiding these two Majorana fermions in this state in here, it's not just giving us a minus or plus phase at the end of the day. Actually, it creates a superposition of this initial state with the state with no Majorana fermions at all, okay? And this is a non-trivial operation then that I'm doing in my logical qubit. Because then if I say that my qubit is this 0, 0, and 1, 1, for any superpositions that I am in this qubit subspace, once I braid these two Majorana fermions in my system, I'm essentially making some pi over 4 rotation in my qubit. and then I'm creating this logical gate or this logical rotation in my space or in my quantum computer to employ in my tasks for the quantum information processing. Okay, and moreover, this is exactly a pi over 4 rotation that you do here, because this is defined by the statistics of these edge quasi-particles. So this is a fault-tolerant operation because it's always going to be very well defined by this angle. Of course, this is also bad because sometimes you want to do some different angle rotations, but then you need to employ different mechanisms as well. And essentially, that's why we want to create these particles for quantum computers, because then we have these protections that we call as a topological quantum computation. Okay, so given that, I think that I said everything that I wanted. And just to say that the main idea or the main concept is that dissipation may not always be detrimental. We can try to exploit this for good purpose. And specifically looking careful for how you couple your system to this environment. Perhaps you can even generate some interesting phases for quantum computers, right? So you can generate what is called these dark states that are actually pure states with possibly many body correlations, topological properties that comes from this frustration-free growth states and so on. And I mean, I think this is a very radically different concept from the usual approach that could have many fruitful results as well. So, okay, so given that, thanks for the attention, everybody. And let me say, also thanks again for the organizers, since this is the last lecture. I enjoy a lot this week, and I hope that everybody had some good time as well. Thank you. And are there some questions? Yes? So no, I think that this part I think that will be easier to implement, because in these optical lattice, for example, you can really create some local potentials in some specific regions in your chain, and then you can manipulate what's the energetic cost as some precise positions there in a way that you could make the fermions or the chain to shrink a bit or to enlarge a bit. I don't know about the T-junction, if you can create this specific geometry, but yes, I don't know. So to manipulate the position of a single edge fermion, I think that it could be more easy to handle. But now you need to have several chains as well, right? It's not just a single chain with edge, you need to have many of them. And then I don't know, yeah, I don't know. I think it's still a challenge, I would say. But I'm not the most expert on these things as well. Okay. Yeah, so I mean, yeah. That's why it's interesting to think on different forms also to generate these particles, because maybe you want platform, you can implement some things much, much easier than others. Yeah, there is always this equilibrium that we should try to put in the balance. Yeah. I'm sorry, yeah. Yeah, so... So I don't remember exactly. Yeah, but I see your point. I see your point. No, I don't remember. I think it was not so hard, but I cannot remember. But I see your point, because in the end, this guy is applying on 2 and 3, right? So it could either create or annihilate this guy here. But at the end of the day, this gamma 1 and gamma 4 will still survive in the equation. No, yeah. But in principle, yeah, because you can even create the density or the unitary operations. This is just 4x4 matrices, and you see everything, how it's acting on all of the bases. But yeah, yeah, I can show perhaps later, but it's possible. It's possible. But I see your adopt also. I had the same. Okay.